Longitude is slightly more complicated, because 1 minute of change of longitude is 1 nautical mile only at the equator. You can see that the distance on the Earth at latitude B between the same change of longitude is less than it is at latitude A, the equator. This east-west distance on the Earth is called departure, and is measured in nautical miles east or west. The equation linking departure and change of longitude is that change of longitude in minutes equals departure over the cosine of latitude. However, there is a mathematical function called the secant, which is simply the reciprocal of cosine. For instance, the cosine of 60 degrees is 0.5, so the secant will be 1 over 0.5, which is 2. So we can rewrite the above formula as change of longitude in minutes equals departure times secant latitude. This gives us a computing method for calculating the change of longitude. SE is coming out of the second stage east-west integrator. SE is nautical miles in the east-west sense. This is departure. We therefore take this departure and multiply by the secant of latitude. Present latitude is already available to us, so the system takes a pick-off latitude from the North Channel and feeds it to a microprocessor, which calculates the secant and multiplies it by the output of the east-west second stage integrator, thereby converting the departure into change of longitude. Let's just sum up that data flow again, because we are going to use it to build on in a future lesson. We have a north and an east accelerometer. They sense every change of aircraft movement and pass it to first stage integrators. The first stage integrators continuously add up these accelerations, thereby converting them to velocities. The velocities are used to calculate track and ground speed, and they are also passed to second stage integrators, where they are converted to distance gone. The northerly distance gone is simply added to the initial position to generate a new latitude. However, the easterly distance gone has to be converted to change of longitude. We need an input of latitude. Fortunately, we already have it. It is the current latitude part of present position in the display. The latitude therefore passes to a secant multiplier. This converts it to change of longitude, which is added to the initial position to generate a new longitude. Because of the speed at which computers operate, this process is repeated many times a second. We therefore have a continuously updated present position. Let's summarize the whole lesson now. There are various different forms of accelerometer, but the pendulous E and I bar type is a fairly common one. The actual mechanization does not need a long vertical bar, and practical accelerometers are usually a rectangular shape, with the long side horizontal. Integrators convert a rate of change over a period of time into total change over that time. It is essential that the accelerometers are mounted on a table that can rotate, pitch, and bank, called a platform, in order that they can be kept pointing north and east. The platform servos have to be rapid response and very accurate, and the platform is heavy. This is difficult to engineer. Consequently, the servos used to wear out quickly on early models of INS. Finally, we covered the data flow from the accelerometers to the display. That concludes this lesson. The next one will cover platform stabilization.